Well, thank you so much, everyone, for being here on this Friday. I know it's a lovely day outside, and we will enthrall you with pictures to make you want to go outside after this talk, too. I have the pleasure of introducing my colleague, Atefeh Hossini. Atefeh, who is right here. You can't see her yet, but you will in a second. She's a PhD candidate in civil environmental architectural engineering here at KU. Before she came here, she did her master's at Nebraska-Lincoln. Atefeh's PhD is exclusively focused on physical, chemical factors and how they affect lakes, lake function, but more specifically, how that relates to harmful algal bloom occurrence, toxicity, magnitude, geographical extent. Usually, Atefeh studies large, shallow, muddy lakes. So think Clinton, Marion, Milford, those sorts of maybe large lakes that you've been to. But today, she's going to do something a little different. And I'll let her explain just how and why these things are different. Atefeh, please take it away.
Thank you very much, Ted, for introducing me. So I'm going to share my screen with you. Hopefully there is no issue with that. Okay. And then talk about my, this is a screen share that, this one. Okay, just a second.
Now, if you go into slide share.
Slide share, okay, make it bigger. Okay, great. So thank you very much, everybody, for coming to my presentation at the end of the semester. I hope everybody is enjoying the weather today. So what I'm going to talk about the sensor-based detection of the deep bloom algae and algal communities. And it's a special case that we did this at the Cross. And the Cross is a special reservoir which is located in the Kansas field station. So first of all, I want to thank you all of the team people that we work together, and there are many people behind this data. So Debbie, Cara, and Ted, my advisor at the civil engineering department, Becca and Javier. You are awesome. You always help me with collecting the data, and I have the privilege to present this data today. So in this talk, I'm going to talk about a little bit about the lake thermal regimes and the light. It's the basic things. I'm going to go through that. And then we talk about the algae and their associated compounds. Then we talk about the lake dynamics that impact the deep blooms. And we discuss what we found at Cross. And finally, we can see how we can summarize. So the lake seasonal thermal regime or stratification, the basic of that is during the winter, the lakes are very mixed and the water temperature is cool. So the spring starts, the air temperature is going up, and consequently also the water temperature increase. So we can see that the top surface of the lake temperature increase, and as we go to the summer, the difference between the top layer temperature and the bottom temperature increase, the difference between the temperature increase, and we can see that the density also is different, as we can know that the warm water are very light and the cold water is really dense. So we can see that there is a separation between the light and warm water at the top and the cold and dense water at the bottom. So usually there is a sharp decrease between the temperature as we go from the top to the bottom. And when this sharp decrease happens, it's called the thermocline, or it's a layer that we can see this separation. And in natural lakes and deep lakes, when this separation happens, it's very stable during the summertime until the winter time is again the turbidity and the wind mixing happening. So, and the basic of the light, so we have the incoming solar radiation reach the lake surface. We basically focus on the photosynthetic active radiation, which is about 400 to 700 nanometer. And once the light reaches the surface of the lake, we have some reflection, we have some scattering due to the water molecules, suspended particles, organic matter. And we know that the algae, they need the light because they are plants to survive. And how much they can tolerate. So they can tolerate between 100% to 1% of the light. And the depth that the light is less than 1%, usually called euphoric zone at the lake. And after this depth, it's really hard for the algae to survive because they need the sun, the light for photosynthesis. So we have these cyanobacteria issues everywhere in this in the shallow and deep lakes, especially in Kansas. Why they call cyanobacteria? So the cyano is the color that it composed of two blue and green color, and when they combine, they call it cyano. So they call algae and they work as algae, but they are basically cyanobacteria. And they are the oldest organism on the planet. They have about like 2.5 billion years of history on the earth. So, and they can produce toxin and other, but not all of them, they can produce toxin and others, only some of them, and they should have the gene to produce toxin and others. And we have about 2,000 to 8,000 cyanobacteria species on the earth. And each of them, they have hundreds and thousands of the strains. So the picture that you can see, this is the species that we found on the cross, and it's Apheniozomenum, if I can pronounce it well. The cyanobacteria toxicity, as we mentioned, some of them, they could be very toxic, and even the toxicity of these species could be more worse than the cobra's venom. So they can also produce toxin and odor if they have the genes to produce this odor and toxin. And it has been found that microcystin, which impact the liver, and anatoxin A and saxitoxin, which has the neurological impact, they could found in the deep bloom cyanobacteria. And why the cyanobacteria, they are very special? Because they have this ability to adjust their position in the water column depth. They have these gas vessels, which are basically the little blooms that they can use to float within the water column. And it gives the cyanobacteria the advantage to outcompete the other algae, which they do not have these vessels. And they can move throughout the water columns whenever it's comfortable for them to get the light or nutrient. And it's a quite big advantage for the cyanobacteria. So usually in the reservoirs and lakes, which are very shallow and eutrophic lakes in the Kansas, we can see during the summer, we have a very calm, warm layer of the water at the top, and it gives the cyanobacteria the environment to accumulate. And if we have a if we have a breeze of wind, that we can see that these scums of the cyanobacteria will be washed off to the shores. So we have these cyanobacteria blooms at the surface in a shallow eutrophic lakes in Kansas. But we cannot see the same thing in Cross, and we want to know why the Cross is different. So the Cross Reservoir has been built in 1991. So most of the reservoirs in Kansas has been built around 20th century. So it does have a very unique environment because it has been built at the Kansas Field Station, and it has the minimal human impact. And it's substantially deeper than other reservoirs of the similar size, and it functions as a natural glacial lake. So it does have usually the lakes and reservoirs depth in Kansas is about 20 feet, but the cross deep depth is 40 dips in the deepest part. And it's acting as a, that's why it looks like a glacial natural lakes. And it has two like intermittent streams going to this watershed through the grassland and the forest watershed, and the majority of the land cover in this area is grassland and forest. So it is a very unique reservoir because it looks like a natural glacial reservoir in compared to the other reservoirs in Kansas. I highlighted this point because that's a very important point, and we come back to this point again. So what is the mechanism behind the deep bloom formation in the Cross? Because the Cross is the only one, I think, reservoir in Kansas that we can see the deep bloom. And during the winter, we see that the water is really mixed. As the summer starts and we can see the top layer of the water gets warm, and we can see the thermocline because the warmer water at the top and we have the cooler water at the bottom. And because this lake is very clear, the light can penetrate quite deep. So we can see the euphotic depth is below the thermocline. So between the thermocline and the euphotic zone, there is a Goldilocks zone for the cyanobacteria to accumulate. They can avoid the turbulence at the surface. And we know that the cyanobacteria, they hate wind and turbulence. So after that, in the early fall, we can see that the weather is getting cooler and the thermocline moves down. So it moves down below the euphotic zone. We know that the cyanobacteria needs light to survive, but they move down with the thermocline because they use the storage of the nutrient to survive, and they can avoid the turbulence at the surface. So because the light is still penetrating quite deep in this lake, they even move down to the lake with the thermocline. But at the late fall, the temperature is getting really cold. We have this turnover in the lake and it's a windy condition, and they are starving for the light. So they come to the surface and they collapse, and we can see the scums of the cyanobacteria on top of the lake. I'm going to show you the picture that we took in 2018 from the blooms comes to the surface, and you can see that these are the dead bodies of the cyanobacteria at the Cross. So what we want to do, we want to do the high frequency measurements. And for the high frequency measurements, we need the buoy. So you can see me with the buoy. This is from different lake, but we have the same buoy at the Cross. And the instrument that we use is the hobo. They call it hobo. It's a pretty cheap instrument in compared to the other field instrument. And it can measure the temperature, the water temperature at every 10 minutes. So we have a very high frequency data. And we need to just install these hobos on the buoy and then leave it. And if we have more hobos, we can capture more of the dynamic in the water column profile. We also did some discrete measurements. So the discrete measurements, we did it with the SECI, which is the pretty normal measurements for the lake measurements. We went to the lake, we did the SECI and the LICOR measurements to have some idea about the turbidity and the light penetration at the lake. But remember, these are discrete measurements. And we have the fluoroprobe to do the algal community, but it's not going really down. So it's most of the time for the epithelium of the lake. So this plot shows the cyanobacteria concentration over the time at Cross. So this is the work that has been done by Kara, and it shows the concentration in 2020 and 2021. So we can see the huge concentration in about July when we have the thermal stratification at the lake. Then I'm going to show you what I did with this all the sensors data in 2020. This is for this year, 2021. So this is the heat map, which represents the thermal dynamic of the lake over the time. You can see the depth on the x-axis, and this is the time on the depth on the y-axis and the time on the x-axis. And you can see this is the Secchi depth, the black line, the black dotted line. The light depth is the blue color, and the triangle, you can see these are the deep bloom measurements that we did. And it is very interesting to see that, okay, when we have the thermal stratification, you can see that it's kind of a stable area in the epilimnium, and then we have this deep bloom during the summer, very close to the thermocline. And as we are going down to the close to the fall, we can see that even the bloom depth past the light depth, and it's getting closer to the thermocline. So the impact of the thermocline on the bloom depth is kind of obvious in this image, but we want to see also what are the other meteorological factors or drivers that impacting these thermal regimes of the lake. And I put the air temperature and the wind speed from the Kansas field station, for somehow there was no precipitation for 2021. So we can see again that when the temperature rise, the rise in the temperature is about 10 degrees Celsius in about second week of June. Then we have low wind and we have a very stratified lake. Again, when the temperature rise in about middle of July and the wind is going down, then we have the very stratified lakes. And this is very consistent through the time. So when the temperature rise, we have a calm condition. And if we could also show the precipitation, I am sure that it shouldn't be so much precipitation in that period also. Then we can see that the lake is stratified strongly. And the strong stratification has an impact on the algal community. So we could see that there is a tug of war between the light and nutrient for the cyanobacteria to survive in this Goldilocks zone. Even we know that they need the light to survive, but we can see that there is a very strong correlation between the peak depth and the thermocline. So it's about 0.8 R square, and it's much higher than the light depth correlation with the deep peak. So we can say that the thermal stratification determines the deep bloom depth because it can regulate the nutrient, because the cyanobacteria, they can regulate their nutrients, and even sometimes they can access to the nutrient from the very bottom of the lake if they can release the phosphate or nitrogen, and they can access this nutrient. And what dominates the presence of the cyanobacteria below the thermocline, it's the hydrodynamic of the lake. So what and I got this awesome award from the KU field station, and what is my plan for the future? We order about 8 hobos in order to install more hobos in the station, the buoy that we already have at the cross, because we want to capture every ½ meter depth. We want to increase the depth resolution, and in order to capture what is going to happen if we have a heat wave and the effect of the heat waves on the bloom depths. Because what we have now is just, we have the hobos at every meter at the buoy, and this resolution is not enough to capture the impact of the heat wave. So if we can increase the resolution of the water temperature, it will help us to forecast the impact of the heat wave. And also I can use this data for modeling using the 1D model to predict the behavior of the lake. So I'm going to summarize everything. So we saw that the deep bloom in Cross is because of the light deeper than the mixing thermocline. We saw that the bloom depths and the size related to the thermal stratification. Also the HABs issue in many lakes, it is not the issue in the Cross because we have the deep bloom in the Cross, and the deep bloom, when it happens, it has the minimal impact on the human health. However, they categorize as a toxic level if they are coming to the surface, but this is below the natural health organization. And the deep blooms have a little interaction with the human contact, not at the surface. So many people, they are not worried about the deep blooms, and except for the late fall when the turnover happens and the bloom comes to the surface shortly. We know that the climate is changing and the lake stability is also changing. We know that these Goldilocks zones are moving, and we want to capture where would be this, where they are going, how the heat waves impact these Goldilocks zones and the location of them and the time of the year that it is happening. So basically, this is everything that I have. And once again, I appreciate the Kansas Field Station for the opportunity to give me to come and talk about my research, also giving me this awesome scholarship to buy more hobos. Even we ordered the hobos are on the way because of the supply and demand issue in the United States. We are still waiting to receive them. And with this, I will take any question. Thank you very much.